All right, good afternoon. Hope everyone's doing well. We will momentarily start our plenary session for the afternoon. And before we begin, a quick announcement. There is a lost iPhone amongst the attendees, we believe. And if it is yours, it is at the ASCE Geo-Institute registration booth. Please go there and pick up your iPhone. It's not mine. I've got mine. So for this afternoon plenary session, we will stay on the wildfire topic. Yesterday, we heard a little bit on the policy side, and today we're going to focus more on some of more of the geoscience and geotechnical side. With that, I'm going to invite Professor Idil Akin from the University of California, Los Angeles, and she will lead this session. Thank you, Idil.
Hello everyone, welcome to the session. I'm Idil Akin, I'm an associate professor at UCLA. Today's panel, we will focus on the geotechnical and geoenvironmental impacts of wildfires. I'm going to start with a brief introduction on the effects of fires on soil hydraulic and mechanical behavior. So why we need different type of modeling for post-wildfire conditions, post-wildfire erosion, landslides, and wildfires, because fires have certain effects on the soils and the vegetation. And then the panelists, which I'm going to introduce in a moment, will talk about the slope stability issues after fires, focusing on erosion and debris flows. And there is also going to be a little bit discussion on the geoenvironmental issues related to water quality problems. When all the mobilized mass gets into downstream waters, it is going to create some further issues. So I classify these effects of fires on soil vegetation as immediate effects and temporal effects. The immediate effects on soil are loss of cohesion when the cementation is gone with the initial combustion. And then we can get a reduction in clay content, especially at high temperatures if the hydroxyl groups are removed from the clays as well. As a result, we may get some changes in particle size distribution. So these effects only happen in the top few centimeters of soils. And then we also lose the vegetation. As we lose the vegetation, the canopy, the protective cover from the canopy is lost. And then we get a loss of root cohesion, and then evapotranspiration decreases because of, again, loss of vegetation. And then we may end up with macropores as the large surface roots are burned. You see some examples here in these photos. Those macropores act as preferential pathways for water and ash to travel deeper in the soil layers. Okay. So there are also a formation of these new materials. I mentioned wildfire ash. It's a very complex material. It's typically hydrophilic, and it can be a continuous layer or in patches. For example, in the Happy Camp image, you see different colors, orange and white in patches. Or in the Bolt Creek site, you don't see it clearly here, but you are going to see in a minute. It's covering the entire surface. And in that Bolt Creek site, I should mention, it's a little bit of an extreme example because it was in the Pacific Northwest, a very wet area that didn't experience fires in many years. And as a result, the ash thickness was pretty high. And you see what type of material we are talking about. This material absorbs a lot of water, and there is water-repellent soil underneath it, so any kind of impact loading results in complete liquefaction of that top ash layer. So as I said, this is an extreme case, but we see ash in smaller thicknesses after fires on our slopes. And this has wildfire ash Typically has an organic and an inorganic component, and it can have many constituents from carbonates, phosphates, sulfates, some amorphous minerals. So typically it retains water and then can reduce infiltration temporarily, but all the properties depends on combustion completeness, the temperature, and fuel type. This is the water repellent soil, an example of it. I also talked briefly about it yesterday. This is typically associated with a condensation of vaporized organic compounds a few centimeters below the soil surface, but also very dry conditions, high suctions, low water contents may appear the soil to be hydrophobic as well. And this acts as a hydraulic barrier. And then we have the temporal effects. So the environments after the fire, the forest environment is very dynamic during that recovery period. We get a temporal root decay, regrowth, ash gets redistributed with water, wind, infiltration, runoff, and then we can get the macropores clogged, and then get temporal changes in soil water repellency. So you see here an example, again, from our Happy Camp site in Northern California. On the left image, you see the site conditions right after the fire. Those ash patches, the macropores are visible. And then in April, you see a little bit of regrowth. Macropores are still visible. And then when we went there in June this year, we don't see any macropores anymore, more regrowth. So this tells you that the slope stability is going to change over time as well, because the environment is changing after the fire. So the panel today will start with Dr. Pete Robichaud from U.S. Forest Service. He's going to talk about U.S. Forest Service post-wildfire erosion prediction and mitigation. And then Don Lindsay from California Geological Survey will talk about rapid assessment and monitoring of post-fire hazards in the 2025 Eaton fire. And then Professor Josh West from University of Southern California will talk about earth, fire, and water, complex interactions that shape post-fire landscapes and their hazards. We are going to leave the questions at the end. We will have about half an hour of question and answer session after the presentations. So welcome and thank you for being here. I will invite our first speaker, Pete Robichaud, for the presentation. Thanks.
All right, thank you. Well, we're going to jump right into this and kind of focus in on not the actual wildfire, but what happens after the wildfire, the post-fire consequences. And from an engineering perspective, it might be something as simple as dealing with a road failure issue after a fire, or as complex as to affecting a municipality's drinking water supply. So there's a whole different level of needs and responses that engineers would be involved in depending on what that fire did. So, speaking of fires, what's natural? Well, wildfires are a natural phenomenon. In the western part of the United States, lightning causes most of our fires. In some portions of the United States, in the west, it's man-caused, man-made ignition. This could be from a utility company. It could be from a prescribed fire that goes array. It could be arson, or it could be some kid who didn't put out his matches after he was playing with his fireworks. A whole variety of sources of that, but even without the human impact, wildfires still occur. So it's a natural process. So that means some of these sediment pulses that you're going to see a lot of images of with the three of us who are talking this afternoon, that's natural. And if you think of the actual landscape and the shapes of our landscape, they're often tied to fire and flood events. So that's natural. So we need to accept that and understand that component, that that is a natural process, and that's not going to go away. If I think of, wrong way, this way. If I think of this map on the left, shows the outline of fires in the last 30 years on a piece of ground in Montana, you can see there's not much that hasn't burned. And what hasn't burned is going to burn in the next 30 years. And then the other thing that's happening that we didn't deal with before is a reburn issue. Places that have burned, they're reburning again within 10 or 15 years, which is not what we had historically thought as the fire interval that we would expect that fire back. So the climate has changed, so therefore the frequency of fire is changing. So what are these wildfire effects? And you're going to hear more of that from each of us today. Increased runoff. So we decreased that surface cover, so the organic material protecting that soil surface is now burned up. Water repellent soils, Idle talked a little bit about that. And just for those of you who don't understand that, during the combustion process, there's a lot of hydrocarbons that are given off. We physically see that with the smoke. It's a lot of hydrocarbons. Well, some of that smoke gets translocated into the soil surface. But we all know that soil is a good insulator, right? If you want to put out your fire, you throw a shovel of dirt on it. It's a good insulator. So the hydrocarbons, they condense as soon as the temperature cools, which is only a few centimeters deep. When it condenses, it coats the soil particles, and it's hydrophobic, it's water repellent. So thus, it changes that infiltration capacity. Well, you change the infiltration capacity of a hill slope, you can see why we get increased amount of runoff that can occur. And then decreased canopy interception, well, you can look at that picture, you can see there's not much canopy left. You don't have to worry about intercepting too many raindrops with that canopy. And then finally, the ET. So if the trees are all dead, that means all the pumps are off. All the trees that are normally pumping water out, they're not there. So my hill slope hydrology has changed. So because of that, we have an increase in erosion, debris flows, and then landslides. But what's interesting about landslides is that they occur usually 5 to 10 years after the fire. All right, so currently in the United States, we have a burned area emergency response process. It's a process where we evaluate every wildfire in the United States above a couple hundred acres. It's done at the federal level and at the state level. Don Lindsay will talk a little bit about that, I'm sure, for California. And one of the first things they do, we have to determine the spatial extent of the soil burn severity, or burn severity of one flavor or another. And what we've learned, if we use satellite imagery to do that, the satellite might capture more about the canopy than the ground surface. So we have to go out to the field and validate what that image is looking like. And we have 5 things that we look at: the color of the ash and the depth of it, the fine roots in the upper surface of that soil, the actual soil structure, the water repellency I mentioned, and then the amount of ground cover left. So there's a field guidebook that people take to the field, has a bunch of pictures that they can use to assess what the conditions look like. With that, they can create this soil burn severity map. That map is important for the rest of the decisions that are going to be made after a given fire. The other component they have to do is evaluate the risk. What would be the impact if we have increased flow coming down a particular stream channel or a canyon? So we need to know what's downstream. Is it just a road crossing? Is it a road that's important to go to the hospital? Or is it the actual hospital? Well, all of those have a different level of risk that we want to mitigate for. Then we have to model the landscape. What do we predict is going to happen? And I'm going to talk a little bit about some of the models that we've developed within Rocky Mountain Research Station. And then lastly, is if we're going to try to reduce that risk, we have to implement some treatments. So we have a catalog, call it a treatment catalog. And this has a listing of all the different kinds of treatments, and I'll talk about that briefly at the end. So we have tools that are out there that are available that might be handy for people if you as engineers have to deal with some of this post-fire impact. Evaluating that risk. So when these teams do it, they kind of have to do a quick assessment and make some decisions because we're not quite sure when that first storm's going to come. So they want to start implementing things usually pretty quickly. So they'll just use a simple matrix that we show in this table of looking at the probability of damage as in the magnitude of that consequence. Is it minor, moderate, or major? And then they will decide, okay, if it's very likely to occur and it's a major set of consequences, then they're probably going to try to implement some treatments. And a lot of that is very relevant here in Southern California after the fires this past year and the amount of infrastructure improvements that they made. Modeling the landscape response. So we've been involved with developing the Water Erosion Prediction Project. That was a soil erosion model. It comes out of the National Soil Erosion Lab in West Lafayette, Indiana. And it was built in the 80s and 90s to basically replace the universal soil loss equation. Well, since that time, it has advanced well beyond its initial capabilities, and including doing watershed response. So we've spent decades working on that, and we have a pretty good tool, we think, that's a physical-based tool to help understand and predict what we think will happen after we have these major disturbances. So I'm going to talk a little bit about these models. All these models are publicly available, so they're free. Your tax is paid for those. All right. What is WEP? It's a distributed process-based model. It does daily and event-based predictions. It uses climate, topography, soils, vegetation in different data layers. In the old days, it might be you'd put in numbers, but now everything is GIS-based, so you put in layers of soils, layers of what we think the climate's going to be for a given area. So it's pretty cool that we've advanced that much in making these predictions. It simulates both saturated excess and infiltration excess runoff. Okay? And in the forest environment, it's important that we predict that base flow and lateral flow because that's critical to get the stream flow correct and to be able to show what the change in that stream flow will be because of this extra disturbance. It predicts both upland, hill slope erosion, as well as channel erosion. And a lot of the soil parameters are based out of the Surgo and Statsco database, but then we have done extensive field work to figure out the parameters that we need after disturbance, so after a fire, where we physically go out and measure some of the erodibility parameters that run the model. And then we provide outputs in graphical table, probability tables, et cetera, to make it easier for users to use the information and make informed decisions. And this is all supported by us at Rocky Mountain Research. So there's kind of like two modes of our tools. We have hill slope scale tools and watershed scale tools. And what we've done is that we designed interfaces to answer specific management questions at those different scales. So I'll talk a little bit about on the hill slope, one, the ERMIT and the WEP road, and at the watershed, we'll talk about the WEP cloud. QWEP is just using the QGIS system, open source, so it's another way to use the tools for those of you who have, are fluent in that. So in this experiment, if we can get that video to work, there it is. So I mentioned that we measure things in the field, so this is us measuring real erosion rate. The metal pipe you see on the right is the rainfall riser, so we just rained on the ground, and now we're putting flow coming down the hill, so we can actually measure the detachment rate of water going over that burnt soil condition. And in this case, we did the rain, and then we did the rill afterwards, and that makes the crew a lot happier. When you do the rainfall and the runoff at the same time, and it's a sunny day and they're getting soaking wet, your crew's not as happy. So we use that to get our parameters that we need to run the WEP model. So what are some of the results? So if I just kind of categorize 4 different conditions in a forest environment, the natural or unburned condition, sediment concentration on the y-axis, basically it's 0, and a low burn severity, it comes up just a little bit, maybe 10 or 20, grams per liter. But if I'm in a high burn severity, we might be up to 50 or 60 grams per liter. So, there you go. There's 50 grams of sediment, and there's my liter bottle. So, I could pour this in there, but then it won't be so good to drink. But I'm talking about this much sediment in the base of this is what's coming down the hill, okay? So you get a feel for the amount that we're talking about that will be coming off of these hillsides because of that fire effect. And then lastly, that skid trail, that's where, you know, for when we're thinking about maybe some post-fire salvage logging, the impacts of that logging equipment on erosion, and because of that extra compaction with the heavy equipment, guess what? We have higher erosion rates too. All right, and so to help people get started with the models, we have tutorials. We have an FS WEP channel on YouTube. So we have all these tutorials so that you can stop and start it and learn different components of the model. We did that during COVID, and it's still very popular to this day. A lot of people use that to learn how to use the tools. So here's an example of one of the hill slope tools, the ERMIT model. On the left is like about a 6-click input screen that the user has to tell us something about the climate, something about the soils, something about the hill slope profile. We run the model in the background for 100 times. We come up with a likelihood of the different rain events that would occur. And then on that graph, if I tried to read that graph, it might be like the purple line. There's about a 20% chance I might get, I don't know, 3 or 4 tons per acre off of that hill slope, okay? So now I have a probability and I have an amount that might come off. Well, if I have something downstream I'm concerned about, down in the bottom table on the right shows that if I put some treatment out there, mulch treatment as an example, I'm likely going to reduce the amount of erosion that would come off. So we made it easy for a user to be able to compare treatments and look at the benefit of doing different treatments to be able to compare that without doing a treatment. Really helps them figure out you know, whether they want to do that or not. So another one of our interfaces, WEP Road, is looking at the road prism. And roads are not affected by the fire, but because of where that road is located, it might have a lot more runoff than it was originally designed for, okay? So what we've done here, we have a simple interface to be able to look at different types of road prisms. So you might have an inslope with a bare ditch or an inslope with a vegetated ditch, and this segment shows you the difference in the amount of sediment that would come off. So again, a real easy interface for people to use. And then we also built a batch processor. So someone who's cunning in their GIS, they can divvy up a whole road network into segments, put it into a spreadsheet, load the whole spreadsheet, it will run everything and spit it back out to your spreadsheet. So we make it easy to be able to do large-scale analysis as well. Web clouds, when we want to start dealing with the watersheds. This is the interface that we have. So you can, on the left-hand side, you can see the green and red little arrows that as you step through each step, it goes from red to green, so you know where you're at. And you have to answer a few questions and load some things for the model to figure out where you are and how to run it. But it's pretty cool. So I can load a soil burn severity map, pick a pour point, or a point of interest. Might be, let's say, a culvert and a road intersection. And I can say, oh, I want to pick that location. I kind of step through all these steps to figure out the land use, figure out the soils, figure out the climate. We have different climate generators that the user can select, so they can look at different likelihoods of events happening. We even have a future climate option in there as well. And then they can run that, and then we have outputs. I mentioned we have outputs in a variety of ways. So on the left would be the annual summary. So what is it, 8 tons per acre per year might be the hill slope erosion rate. But if I'm thinking of a culvert, and whether the culvert's big enough or not, I might want to look at the peak discharge, and I might want to look at a return interval. So we have another table that would give them return intervals and the volume of water we would expect. That's a much easier way to figure out, is that culvert going to be big enough, or is it going to get overtopped? Then I also mentioned the lateral flow and base flow for forest conditions. Those are important pieces. And when you look at our results, we always provide that information as well. To get the hydrology right, you need to include those. In some of the other models, they don't do that, but we feel that's an important piece. So in 2022, the Hermit Peak Calf Canyon fire was in New Mexico. And the issue with that fire, not only was that it was a prescribed fire that got out of hand that caused that fire, but it also, the source area of the drinking water for the city of Las Vegas, New Mexico. And that's a picture of their reservoir full of black water. So we had been working on developing an ash transport model. And so the purpose of this model is to be able to predict the impact of that ash on the water quality parameters, okay? Well, to do that, you have to kind of think of what's involved. Well, one, we need to know how much ash is out there. We need to know where that ash is and the likelihood of that ash being transported into that stream channel. And then in the stream channel, it's going to go down to that reservoir. So we started off by developing ash load maps using satellite imagery. In this case, I think it's a world view imagery. And we're able to predict what the depth of the ash that's on the site with this imagery, with some ground validation, so then we can get an ash load. Well, one of the things that we learned early on, all ash is not created equal. There's a bunch of different types of ash out there. So the little vials are from, I think, 15 different wildfires that we went to, and I got 15 different samples of ash. And then you do the chemical analysis and the spectral signature of it, and you realize that, yeah, it's not all quite created equal. So we developed this asher, this ruler, that at least gives us 8 categories of color of ash. And that color is important because that tells us something about the combustion process, how complete it was, and what the mineral content of that ash is after the fact. Then we had to figure out, how do we transport it? So we did indoor experiments and then outdoor field experiments to figure out how much of that ash actually gets transported and how far does it go. So kind of an involved process over the last several years getting this information. The goal is to be able to give us an ash delivery. What's the probability we're going to get 200 tons of ash into that reservoir after this fire? And then the next step that we go is to be able to say, well, what's going to be the chemical component and the nutrients that are in that ash that are going to get into the water? So maybe it's, let's say, silica or calcium or iron that's going to be in it. So we're able to now predict what we think those changes in those water quality parameters are. Right now, we're validating this with some reservoir data from Fort Collins and Greeley, and then also Las Vegas. The other thing that came up as we started doing more of this work is scale. So we're working with the WEP model up to about 10,000 acres in size of a watershed. When you get beyond that, the channel processes are pretty dominant. So to try to address changing scale, we worked with the Corps of Engineers, and we're working with the HEC-RAS model to be able to take the output from WEP as an input to the HEC-RAS, and then be able to use their mesh making and their transport equations to then transport that ash and sediment into these larger watersheds. So that's work that's ongoing right now. I mentioned something about reducing the risk. So how do you reduce that risk if we know that all these predictions, we say, oh my word, there's going to be a ton of sediment coming down, debris flows, what are we going to do? So there's 3 categories of kind of treatments you can deal with. Hill slope, dealing with it at its source. Road treatments, because the road prism is already built, and it's now affected by that fire. And then channel treatments. And I'll just briefly mention that we have a nice catalog that talks about all the different treatments. GeoBrig is out there in the exhibit hall talking about some of their debris catching fences that they sell that are often used after fires. But we've done a bunch of research on how effective all these things work. So in this case here, looking at some of the hill slope treatments, some mulches you might apply, or a seeding treatment, or a log erosion barrier that you might apply, and how well they all work. With road treatments, it might be maybe just armoring the inlet of a culvert, or changing the size of a culvert. Or maybe we can remove it temporarily, that we don't really need that road for a 5-year period. Let's take it out, let the natural processes occur, and we'll put the culvert back in next time we need that. So kind of in summary, what I kind of talked about is wildfires, that they are natural, they are going to continue to occur. The amount and rate that we have had in the last 10 years, I foresee staying about the same during my lifetime and your lifetime. I don't think that's going to change anytime soon. There is a process to evaluate these. They make a report, BEAR report, that's available, so that if you get involved with any post-fire work in one way or another, there's a lot of tools that are out there. I mentioned our FS Web tools, and I also mentioned some of our publications. So there's a lot of things that are currently available to help assess these conditions. So with that, I think I'm going to turn over to Don, and he'll continue on the way.
Good afternoon, everyone. Yeah. So I thank you for this opportunity to give a presentation today titled Rapid Assessment and Monitoring of Post-Fire Hazards in the 2025 Eaton Fire. The focus of my presentation and the outlines presented in this slide, I'll first introduce the Eaton Fire. I'll then introduce you to what's referred to as the Watershed Emergency Response Team, or WERT, team assessments. I'll then touch on monitoring work that our program and partners are engaged in performing to improve the science. And then we'll lastly touch on future work to expand our ability and improve prediction of post-fire hazards. So the Eaton Fire started on January 7th of 2025. It burned approximately 14,000 acres. It was above the community of Altadena, and unfortunately it resulted in approximately 1,000 homes being damaged and 9,400 homes being lost. And also, unfortunately, there was approximately, there was 19 reported fatalities. The fire burned at mostly a moderate and high soil burn severity, and it burned in rugged terrain of the San Gabriel Mountains. This is an oblique image of the Front Range above the communities of Altadena, showing the relative relief. It's a large amount of relief of the burned hill slope. So you can see that the terrain is very steep and rugged. And it spills out onto alluvial fan surfaces that now are occupied by a densely populated built environment. Because of the presence of alluvial fans, it indicates that this area is pretty frequently exposed to flash flood and debris flow processes. As a result, the LA County has installed a network of debris basins along the Front Range, right, separating the mountains from the built environment. And despite the presence of the debris basins, the occurrence of the burn severity upslope, we identified that there is a potential still to the community of the downslope areas. And as a result of that hazard, or that potential hazard, WERT team, again stands for Watershed Emergency Response Team, was stood up. And WERT teams are conducted by the California Geological Survey and CAL FIRE. Their main objective is to perform a very rapid assessment that generally takes just a couple of weeks to perform. And the main objectives include identifying where values at risk, we call them VARs, which is things of structures, infrastructure, things of that nature that could be impacted by the burn scar effect. Second is to identify just what the burn scar had on increasing post-fire hazards. That includes flood flow hazards, debris flow hazards, landslide hazards, rockfall, things of that nature. We then oftentimes make recommendations to help mitigate the hazards to the values at risk, and we communicate all of our findings with, again, a very quick turnaround time to local stakeholders so that they can take the information and implement it in a response plan. Oftentimes, this requires a lot of interagency coordination and cooperation. On the Eaton fire, that was very relevant. And here's just a short list of local, city, county, and state and federal partners that participated in some form within the WERT assessment. Now, the area of the San Gabriel Mountains upslope of the within the Eaton fire burn scar it's not uncommon to have fire and post-fire impacts. The bulleted list to the left here, it provides a list of documented impacts inside the burn scar and the surrounding area. I'll just focus on a few. The top photo shows the 1993 Kinaloa fire that in 1994, the following winter, there were flood flows, debris floods, and debris flows that propagated down Pasadena Glen Canyon. And the debris got racked up on a debris barrier that was installed immediately following the Canola fire. The photos on the bottom part of the slide point to areas that were damaged by overtopping flows from the Moala debris basin in the 2009 station fire. Ultimately, 40 homes were damaged during that overtopping event. Now, to assess debris flow hazards, we commonly rely on two different models that were produced by the USGS. The first model we refer to as the Staley model. This model predicts the debris flow likelihood given based on the magnitude of short duration rainfall. And the second model, we refer to it as the Gardner model, and it predicts the debris flow volume or magnitude of an event. And it too is a function partly on short duration rainfall. Here's a map on the right showing modeled results of the USGS debris flow models. And across the range front, you can see that we see a lot of reds and oranges. This indicates relatively high debris flow likelihood shown with the squiggly lines that are along channel segments, and then also colored basins that shows the combined hazard of debris flows. And you can see we have generally moderate to high potential hazards here at a relatively low rainfall intensity. And this map is generated based on a 15-minute duration storm with a 24 millimeter per hour rainfall intensity. And that roughly equates to approximately 0.24 inches accumulation in 15 minutes. So we have these USGS models that indicate that the area is prone to debris flowing. And this is confirmed through field observations that the work team made. A great example is just a recognition of very steep slopes that have the vegetation removed, so raindrop impact, a lot of soil is exposed on the surface, and there's a readily supply of soil that can be eroded off the slopes. Also present, which is very common in the San Gabriel Mountains, is what we refer to as dry ravel. that forms as vegetation is burned, and that vegetation helps support sediment that have accumulated on the up slope side of the bowl of the sediment, and it allows the vegetation is removed and dry gravel is allowed to cascade down the slopes. In the Eaton Fire case, much of the low order drainages were completely infilled with dry gravel, and in some cases several meters deep. This sandy deposit can be easily mobilized during a runoff event. It can bulk flows and trigger debris flows. A great example is, again, taking you back in the Pasadena Glen Canyon, where we have the debris rack that today, or just after the fire, demonstrates the presence of past debris flow events with poorly sorted debris upstream of the debris rack, as well as damage to the pipe debris rack infrastructure. Now, a big part of, I've touched on debris flow hazards up to this point, but a big part of the post-fire work assessments is to quantify post-fire hydrology. And what I mean by that is the increase in post-fire flows due to the fire. To do that, the work team evaluated approximately 12 basins, and we focused our attention on basins that were not protected by debris basins. The distribution of the basins is shown on this map. And here is the output of some of the hydrologic modeling that we performed using emergency methods or models or approaches that are explicitly used for emergency processes to estimate the post-fire flows. Much of the data is disclosed to the public and to end users as a flow multiplier. And in this case, it's the M, the blue M. And the flow multiplier is a function, again, of the increase in runoff and sediment bulking caused by the fire. And you apply this flow multiplier to a pre-fire flow condition to estimate what the post-fire peak flow would be. In this example, we have a number of basins, all of which have flow multipliers less than 11. I want to bring your attention back to Pasadena Canyon, Glen Canyon here. Again, the basin here was burned mostly at moderate with a little bit of high. And the flow multiplier that was calculated using the emergency methods in this case was 6.5. So kind of remember that value. And just for reference, here's some map of the downstream area of Pasadena Glen showing the values at risk shown in a polygon, downslope of modeled high debris flow prone or hazard slopes. And then you see some of the infrastructure that spans the channel just downslope of the mountain front. It includes crossing structures and residential structures immediately adjacent to the channel. And for reference, I just want to draw your attention to this wood bridge because it will be shown in subsequent slides. The WERT assessment within the Eaton Fire identified 127 VARs. 82 of those VARs were isolated individual points. It could be a house, it could be a culvert. 45 of those VARs are polygons, so it's a polygon that may wrap around and include groups of values at risk. The data is presented in the report as a map book. The photo on the left or in the central part of the slide is a map book showing the individual panes. And the figure on the right is a map pane that shows the level of detail identified and presented in the WERT report. The final WERT report was completed and submitted to the public on February 4th. Included in that WERT report was coverage of our methods that we applied, our findings, our recommendations to mitigate hazards, post-fire triggering thresholds, and as well as the MAP VAR products that I described to you. This QR code does provide an active link to access the Eaton Fire WIRT report. The information provided in the WIRT report was shared with the local stakeholders, in this case LA County, who then used that information to help define a response plan around. This is an image that I clipped off of their webpage that identifies 3 phases ranging from green to red of a potential response plan that's geared around a type of storm event. So now the WIRT report's been implemented, the counties developed their response plan. Now it allows us to pivot outside of WIRT and focus on performing post-fire monitoring. To do this, we frequently collaborate with local collaborators. In this case, we collaborated with the USGS, the US Forest Service, and Caltech. The initial monitoring plan was to install stream gauges and rain gauges along key basins within the Eaton Fire. And also Caltech was going to be producing repeat drone-based LiDAR surveys to quantify change. However, the area was hit by storms. First storm occurred on February 13th. This was the largest storm that impacted the burn scar. It resulted in widespread above threshold rainfall across the mountain front. The second storm that I'll talk about occurred 1 month later on March 13th. This storm was smaller, almost half the total rainfall occurred, and the triggering rainfalls thresholds were just exceeded in a smaller number of basins, so it wasn't a widespread storm event. The February 13th event, we utilize it to test the accuracy of the USGS debris flow likelihood model. So looking at the map inset in the upper right-hand corner, you can see that there's a lot of reds. It indicates across the mountain front basins with, on average, 80 to 100% debris flow likelihood for a rainfall event of around 44 millimeters per hour in a 15-minute duration. It's about 0.4 inches in 15 minutes. That is approximately the same rainfall rate that was observed on February 14th on average across the mountain front. Despite that, the models indicate high likelihood of debris flow occurring. Our mapping following the February 13th event only identified 4 basins that we would characterize as meeting the criteria that would be associated with a true debris flow. So in this case, we conclude that in general, the Staley model overpredicted debris flow likelihood. Now, these events, the February 13th event also mobilized a lot of sediment through just debris floods. This is a sequence, or shows 2 photos. The photo on the left is just prior to the storm, and the photo on the right is just after the storm. And as you can see in these photos, the Sierra Madre debris basin completely filled in during this event. To quantify the impacts of the February 13th event and look at the sediment yield coming off these hill slopes, Caltech did repeat drone surveys using LiDAR of 14 basins along the mountain front as they dewatered. They concluded that, based on their analysis, that on average, the basins filled in to within around 50% of their design capacity. Now, we used individual basins or gauge data to identify rainfall intensities to these basins and use that information to calculate the debris yield by applying the Gardner model. We then compared the Gardner model against the measured results of the Caltech study, and I identified that on average the Gardner model overpredicted measured volumes by a factor of 1.45. So now I'm going to pivot to, before we were talking about the debris flow models, now I'm going to pivot to post-fire hydrology. To do that, again, I'm taking you back into Pasadena Glen, and we have the bridge that I pointed out to you. The photo on the left is just as the flow started to increase. The photo in the middle, it captures the peak flow event at around 5:10 p.m. And then just about 16 minutes later, the flows completely receded, exposing the engineered concrete line channel. We used video imagery to quantify the velocity and depth of the flow, and using the wetted cross-sectional area, calculated the peak flow for this event at 2,200 CFS. On February 19th through the 20th, we finally got permission to install our monitoring equipment, and which included installing stream gauges in Pasadena Glen. Here's a look at some of the stream gauge equipment. This is all non-contact stream gauge equipment spanning the engineered drainage. Then on March 13th, the March 13th storm repeated a flow event in Pasadena Glen. Our sensors picked up the flow event, and we calculated a peak flow estimate of around 1,400 CFS. So now in summary on the hydrology, we have two flow events, one at 2,200 CFS and one at 1,400 CFS within the Pasadena Glen channel. This equates to flow multipliers of 52 and 33 for the two storms respectively. And keep in mind, we had previously calculated a flow multiplier of 6.5. So our emergency methods underpredicted the actual flow multiplier by a factor of about 6.5. So to wrap things up, I'll walk through our findings and provide a summary. Finding one, in general, the Staley model overpredicted the debris flow likelihood for the February 13th event. The same can be said for the Gardner model. It overpredicted the debris flow volume by 45%. This allows room for future work to evaluate and revise current post-fire debris flow likelihood and volume models. And then the third finding is the fact that our flow multipliers well exceeded the predicted values used in our emergency models. So again, this provides an opportunity that current post-fire hydrology models can do a better job. And I'll end by stating that the USGS currently has revised volume models in review and a revised likelihood model that is soon to be submitted for soon. And then touching on the post-fire hydrology element, that's going to be a main priority for the CGS BWG program over this winter. So with that, I would like to introduce Josh.
Hi, everybody. Well, thank you to the organizers, and thank you to the prior speakers. It's a pleasure to be here and part of this afternoon's discussion. I'll try to keep things relatively brief so that we have plenty of time for discussion. I'm sure many of you have questions for the speakers who've preceded me. My name is Josh West. I'm a professor at the University of Southern California. I'm not an engineer. Whoops, I'm going ahead already. Let me see. I'm not an engineer. I'm a professor in earth sciences. And what you've heard before me, descriptions of some of the operational models that are available for helping to understand and assess post-fire hazards, and particularly debris flow, runoff, flooding, erosion, and so on. I'm going to highlight what I think are some of the big open questions and some of the really fundamental aspects of the science that we don't understand fully that can perhaps help to inform improved physical models that can address some of the issues that Don described in terms of applying some of the empirical logistic regression approaches, for example, that you saw as implemented in the Eaton fire case. So I'm gonna highlight 2 or 3 of those areas in particular where I think we still need to understand more, and I'm gonna try to describe why. So the first of those comes down to this kind of conceptualization, which you've heard a little bit about, in fact, you've heard a fair bit about from those who came before me. This is a graphic that's produced from the National Weather Service, for public sort of appreciation and understanding, which really shows that development of a water repellent layer and the importance, in fact, the key role of that water repellent soil as being the cause of flooding after wildfire, right? So you can sort of follow along on this graphic. This basically illustrates what you heard others talking about earlier in this session. It's not just the Weather Service who produces this. FEMA produces a version of this. It's a little more complicated, but it all has the same thing in there. Number 2 on here is all about the development of that water repellent layer and the importance of that layer in the soil, reducing infiltration capacity and allowing water to be basically conveyed very rapidly, effectively, as surface runoff into streams and rivers. So the reason that I'm going to ask you to think carefully about that model, and not that there aren't aspects of it that are right and apply well, but the reason I'm going to ask you to think carefully, and that I think as a research community we still have a lot to understand, comes down to this study that I did with a number of different collaborators. Marin Clark, who's in the room, Francis Rengers from the USGS, who couldn't make it here, but was also a participant and co-author in this. This was done after the Bobcat fire, so this is the footprint of the Bobcat fire, which was in the San Gabriel Mountains in 2021. We studied 3 catchments, in fact, but the 2 that you see here are sort of a set of paired catchments, one burned and one unburned by the Bobcat fire. You can see in the middle panel, panel C there, the difference in burn severity, one not burned or very, very little burn area around the perimeter, and one severely burned. We looked in detail at the hydrologic response of these 2 catchments following this fire through a couple of, I think, lenses that had not been as widely applied in this context before. One of those was using electrical resistivity tomography or electrical resistivity imaging, which I'm sure many in the room will be familiar with. What you see here are panels showing the change in subsurface resistivity in the unburned catchments on the left side of this figure, and in the 2 burned catchments. So as I mentioned, we actually studied 3, but you could think of these, the 2 burned catchments were very similar. There was one with a different aspect. What I want to draw your attention to is that this really shows the change in resistivity over time from a baseline immediately after the fire in the unburned and the burned catchments. The first thing, if you just look at this, what stands out are the low resistivity or the decrease in resistivity that primarily occurred in the burned catchments, not the unburned catchments in the subsurface. You also see a drying effect in the middle panel. So I should say that the top panels show the end of the first water year, sometime in the April of 2021. The middle shows the end of the dry season following that summer. You see the pronounced drying in the unburned catchment. That's vegetation effect, right, pulling out water. And then you see another water year, the sort of second water year in the bottom panels. So the takeaway I want you to leave this figure with is that there was a big change in the subsurface in the burned catchments. And if you think about the model that we just described of this sort of Teflon-coated catchment with this hydrophobic layer, that wouldn't really jive with this image of substantial changes in the subsurface in terms of interpreting these changes in resistivity as increased moisture storage in the subsurface in the burned catchments that we don't see in the unburned catchments. So if anything, it looks like in the post-fire landscape, we're facilitating infiltration of more water during the rainy season compared to the unburned. That's very contrary to the idea that all the water is just being shuttled off by these hydrophobic layers. All right, now I'm going to show you this figure, which is complicated. This is using the oxygen isotope composition of different waters over those same 2 water years as a tracer of what happened to rainfall that was falling on these catchments. So water isotopes, the oxygen isotopes in water, you can think of as just a fingerprint that is carried by precipitation and varies, as you see in the blue dots on here, varies from one storm to another. And that fingerprint is carried through as the water is stored and released from watersheds. It's a widely used tool in all kinds of different aspects of catchment hydrology. The application here that's interesting is that the streams in both the burned and the unburned catchment respond almost identically to different storm events. So that is to say that there's little difference in the signature. If you like, we sort of basically put these natural tracers into the rainfall on these two catchments, and there's little difference in the signature that comes out in the stream flow. That really implies that the proportion of water that's coming from groundwater versus surface water in those 2 catchments, those 2 streams, is very similar. Yet there's a 10-fold difference in the amount of discharge between them. So again, if this were all rapid conveyance of rainfall from your Teflon-coated hydrophobic catchments, you would not expect the same partitioning in the unburned and burned catchments between runoff from precipitation and what's being pushed out from groundwater. Okay, so these 2 pieces of evidence, and I'm happy to talk about them more with people afterwards, but these 2 pieces of evidence have, I think, asked us to think really carefully about that model, at least in this site, about that model that you see in the middle here, where burned catchments are dominated by overland flow as a result of water-repellent soils. That isn't to say that water-repellent soils are non-existent. You saw images of water-repellent soils. They form, they're there. I haven't shown a slide of it here, but we measured the infiltration rates in different portions of both landscapes, and there are places with very low infiltration rates, very water-repellent soils in all of the burned and unburned catchments, right? So there is water repellency happening, but it doesn't seem to be the dominant process, at least in this setting. Right? Otherwise, how do we explain the resistivity and water isotope data? So we propose that actually there's much greater infiltration into the subsurface, but that the big change that you may notice when you compare panels A and C on here is the change in evapotranspiration. So you have a much reduced evapotranspiration, and it's changing the capacity of the subsurface to hold water, and that's the big contributor to the increased discharge post-fire. Okay, so that asks, when we look at this, I mean, this is really intended for the public to understand flood risks are real after fires, fine. But when you think about the translation of this into the kind of models for post-fire hydrology, for post-fire flooding, it does matter what the mechanism is, especially if we're trying to aim for sort of physically based models. Right? So I would argue that post-fire flooding may have more to do with loss of vegetation and less perhaps to do with hydrophobic layers that are there, but they may have less of a role to play in post-fire flooding, at least in some locations. And I'll show you one other example where we're testing that, because we've only done that at one site, right? So you could say, well, this is unique to that location in the San Gabriels, and it may well be. But we think this is really important, and it may be important for the immediate models of flooding, but also for the contribution to the long-term landsliding. Somebody mentioned that shallow landsliding increases 5-10 years after fires, and maybe this increased storage of water in the subsurface is a contributor to that. Okay, like I said, we are investigating this further following the Palisades fire. So this is an image of the footprint of the Palisades fire just up the coast here. Just at the bottom of this image, to orient you, is the city of Santa Monica. So the city of LA is just to the east, to the right of this image. We're using this as a template for looking at how this hydrologic response might vary across a range of different settings within a given fire area. This gives you a sense of the sort of variability even within one part of that catchment in terms of the preliminary electrical resistivity imaging results. And perhaps, we're trying to do experiments with these ERT imaging where we look, for example, where one slope has a lot of rilling that's formed and another has remained vegetated. This is all very much work in progress. I should have said this is all supported by this group center that has recently been supported by NSF, and then if you stick around for the next session, Marin Clark will give you a lot more information about. If you're not here for that session, encourage you to look us up on this URL. Talk to Marin, Demetrius Ekos, myself, and others who are here about it if you're interested. Okay, so I've talked to you about flooding. Let me talk to you a little bit about one of the questions that I think is very open and prime for additional fundamental research, now related to the sediment hazard cascade portion. And that has to do with the debris flows that you've heard described by others, Don in particular. A lot of work on this motivated by the station fire that Don mentioned, but also by the tragic Montecito debris flows in 2018. So let me pose you this, that one of the big open questions remains what the source of sediment for these debris flows is. And so Don talked a little bit about the accumulation of dry gravel and showed an image that looks a lot like this. This happens to be from a recent book chapter in this book on post-fire debris flows. Good book, good resource to look at if you're interested in some of the ongoing work on this topic. You also saw from Pete, I think, some images of post-fire rilling or some experiments that the Forest Service has done on post-fire rilling. These appear to have quite different roles depending on where you are. So for example, in Montecito, it looks like most of the sediment came from post-fire rilling, at least based on the analysis that was done with the data that they had. Whereas in a lot of cases, the San Gabriel Mountains, like after the Eaton fire, a lot seems to come from dry gravel. But we don't really know which one matters the most. Maybe we have some anecdotes, right? Like Montecito at the one end, San Gabriel's at the other. But we don't know when, where, and why those things vary. Like, why is it that you would have dry gravel be the most important in one place? Why would it be that rilling is most important in another place? And you might say, well, that's like a fine curiosity for scientists who like to do their academic thing. But I do think it's more than just a curiosity, because in places that dry gravel dominates, one could predict the total volume, for example, that Don was after, based on the amount of dry gravel that's accumulated after a fire, before a storm, right? You could just go in and measure, use topographic change detection, measure how much dry gravel there is, and say that's effectively going to be the size of your debris flow, or the maximum size of your debris flow. Where rilling is happening and a major contributor to sediment, that's not the case. And of course, this also matters if we have changes in fire frequency, because sediment supply becomes a key limiter, right? Like if sediment supply from dry gravel is a limiting factor, it's going to change how changing fire frequency may influence whether you have more larger debris flows. So one of the things we're doing at the moment is working across this Palisades fire footprint and trying to understand where dry gravel dominates, where rilling dominates, and why you see a gradient in those, because this is one fire where we think we have that kind of gradient. So rather than comparing Montecito and San Gabriel, completely different places, completely different storms, this is one location where we think we have a gradient within one fire footprint across these two different processes. I'll just give you a little snapshot of some of the LiDAR change detection that Sulgi Moon and her group at UCLA have been leading across this gradient. Topanga Canyon on one end, where does seem to be dominated, or at least there's a really important role for dry gravel. And here you see topographic change detection maps after the fire but before the rain, and you see the channels that are loaded with dry gravel in the blues. And then after the rainstorm, those channels get evacuated, and the larger Topanga Canyon channel in the middle of that image gets filled with sediment. That's in the far west of the fire area. Further to the east in Rustic Canyon, you don't see anything like this. You still had big floods, big debris-laden floods, probably not what you would maybe not categorize as a debris flow, but the sediment there was sourced dominantly from rilling. So now the question is, why? Now we can go in and look at this and say, okay, what is it about the geology, about the topography, otherwise that's causing this range? And that's work that we're in the middle of doing. I will just point out that this kind of insight that you see from these change detection maps is only possible because we were able to capture post-fire, pre-rain topography at very high resolution, right? So immediately after the fire, thanks to the company NV5, many of us were trying to scramble to get this data. NV5 were the first there and got a great data set that we've never had in prior studies, right? So being able to capture these like high temporal resolution DEMs, airborne as well as UAV, has been a really important resource and one that we hope that we can continue to be able to capture. I'll just point out that, together with the group at UCLA, there's a big effort to do a whole bunch of other monitoring, including putting in debris flow stations in this area, and IDL's involved in that. And there's a lot going on. So if you're interested in this particular event, certainly a lot happening in tandem with what Don described for the Eaton fire. Okay, so in the interest of time, I will leave it there. Just posing these couple of questions that I think we still don't have really good answers to. I'll add a third. I don't have time to go through the slides related to it, but I'll add a third, which is we don't really know how long these effects last. So we sort of have a canonical view that post-fire debris flows last for 2, maybe 3 years, maybe out to 5 years. But I think there are cases where you see fire footprints that have debris flow activity longer than that. And how do you attribute that to the fire or not is a really big open question. So hopefully that gives you a sense of some of the things that are on my mind and sort of areas of active research, obviously potentially, hopefully informing operational kind of forecasts that you might use as engineers, but that give you a sense it's not all completely solved. Thanks.
Thank you, all the speakers. Before starting the Q&A session, I want to acknowledge Ian Floyd. We planned this session together from Ian Floyd from USAID's Coastal Hydraulics Laboratory, but unfortunately he couldn't make it because of the shutdown. Similarly, as our initial speakers, Nawab Pradhan and Francis Rangers, they couldn't make it. And thank you, Josh, for joining us in a really short time and for the great presentation for everyone. Okay, so we have the microphones and happy to take questions now.
Thank you. Very impressive presentation. Thank you very much. I'm from Tokyo, University of Tokyo. I also talked with Edil yesterday. See, every summer when I saw the television about the wildfire about California, I was thinking maybe one day we come to Tokyo or come to Japan. But actually, this year, the summer, we actually had, I think it's 2 cases, small-scale wildfire. And one of them, if I remember correctly, should be lasted about 1 week. I hope not, but I guess this kind of case would increase in Japan. So I want to ask, because I don't think we have a lot of research on that one, so I want to ask any comment or suggestion, see if we had or if we expected to have such an event. What should we do in terms of, say, pre-research or post-research? If you can give some suggestion, it will be very great. Thank you.
Go ahead. Yeah, well, welcome to the new world. Yeah, so fires, I've done some work in South Korea, helping them address their fire issues and post-fire issues, and they have, again, similar scenarios. We didn't expect the fires to occur. They happen. We get these larger debris flows. It took out a major highway. We never had that before. What should we do in the future? So, yeah, a little bit of pre-planning. We've given you good examples, all 3 of us, of the things that can happen. These 2 focused mostly in California, but throughout the western United States, fire and flood, fire and debris flow, fire and landslide definitely occur. Take from what we've learned and try to apply that to your country and your conditions, because you're probably right that you're going to continue to see increase in the near future. Go ahead.
Sure, I'll just chime in and say that I would, like Pete just mentioned, learn from others. I would start by doing a thorough desktop review of what research is available in your area and elsewhere, including in the States, and then see what they have found to work, and then take advantage of that, build around a network of people that come up with a similar terminology, similar game plan of what metrics to measure and quantify and how those measurements are going to be made, so that you can maximize the effort to leverage it down the road to make, more informed empirical correlations. I think that would go a long ways.
I think one of the things you may have gathered from listening to the three of us is there's a pretty mature infrastructure in the U.S., right? Right from the emergency response teams that are ready to go day one, efforts to collect topographic data as soon as possible, through many of us working like on longer term, following that over a much longer term research-wise. So, I think it is probably as much as anything else about getting people together and getting people interested and aware and ready to play roles across that spectrum, right, from the immediate aftermath of a fire onwards, so that you can understand the scope of the problem for you.
It's not on.
I'll hit this gentleman.
Got it on now? Is it on? Yeah, here we go. As quick as possible story. I've got a house in Ruidoso, New Mexico that's experienced all the fires and the floods over the last 2 years. So my cabin's on the edge of a creek. In 2024, we had the fire and then floods immediately after that. The following fall, the city officials came in and cleaned up all of the debris up and down the creeks, including these really large rocks and things like that were in the bottom. After the first year's flood, it was rough and coarse, and after they cleaned it up, it was as slick as it could possibly be. That creek bottom was slick, and there was nothing rough whatsoever on that. Then, that was in the fall of 24. Then we've got the rains that came again this year. Now they're worse. The stream bottom was the same depth after the floods in 2024. After they slicked it up and it rains again, you have the second floods, it took 2 feet off of the bottom of the stream. My house sits up I'm on the point bar side on the inside, and it took 2 feet off for your coming landslides. Now you've taken the toe out of the bottom of this thing. The point was here, it wasn't necessarily the flood, it was them coming back in and taking that courses off. And I hadn't thought about this before until you start thinking about these other things. But you think about how much energy it takes to move those rocks and move that material that the city officials did instead of the stream, right? And then as your streams are moving in and around the brush and the material that's burned, rather than just to add to the hydrophilic soil, it's also the amount of energy it takes to move even downhill, and the distance, just the distance to move it, and then the moving of those large rocks, which contributes to it. And I had the benefit of watching this over a year and a half of what they did, and I'm not an engineer, so I'm sharing this for the other engineers, is to be careful what you do too. You can contribute to it, right? And that's what I saw. I saw that it was much worse, even though they meant well, it was much worse after they slicked up the whole stream. So watch for that.
Okay. Any other questions? I have a question, actually. So after all this research that you've been doing for many, many years, what do you think are some of the biggest challenges that remain, and how we can address to those challenges? Maybe not how yet, but what are the challenges?
I can go ahead and start. One of the main challenges that we're faced is just being timely with being able to install the instruments. We have established a good working relationship with the Forest Service and other public landowners, but even working with under a favorable relationship condition, there's been times where we're 3 to 6 months waiting period to get the green light to go and install equipment, and I think there's an opportunity there. If we can expedite that, that would allow us to not miss storm events, especially it's the first 1 or 2 storm events that really interest a lot of us, and we want to capture those.
Go ahead.
I think I sort of summarized in my talk what I think at least are the scientific challenges. I agree a lot of the logistical challenges have to do with capturing, those sort of, those perishable data, especially, we get later season fires and, the fires this year, as Don described, the rains in Southern California came very quickly after them. And, but I would say another, sort of logistical challenge we have is in trying to track post-fire hydrology. It's really hard, to install instrumentation. A lot of instrumentation that you think of as like standard, stream gauging instrumentation doesn't survive. And even collecting samples, the study I showed with using oxygen isotopes in water, we had to camp out next to streams, all night long, collecting samples every 20 minutes. You have to find sites that are safe to do that. A lot of the sites we're working at now aren't safe to do that. So there's a lot of, actually the logistics of studying these in the field is actually quite hard.
Yeah, and I'll just build on what Josh just mentioned. I showed examples of non-contact stream gauges. Those are supported above the channel, and we have pivoted to going that route so that we don't lose data, because we've lost a fair number of instruments during the actual event where you have maybe scour that occurs that may be inside the channel 3 to 4, meters at times. So.
One thing none of us really addressed is the longer-term landslide issue.
Yeah.
That I think there's still fruitful for research activities. So if you think of what do I mean by long-term landslide hazard? We talked about the change in the hydrology on the hillside, but then with the trees and they die, the root strength is now gone as they decay, so that roots that were anchoring a lot of that soil in place is no longer there. And so 5 years, 7 years later, we get a slope stability issue. And there's been research done on that from road on steep embankments and stuff over the years, but it hasn't really been tied back to the fire effects. And, how long does it take for the new trees to get established that their roots would actually stabilize that slope? So they're shallow in the beginning, but I need deeper roots to stabilize. So I think that's an area that still needs additional geotech type research.
Thank you.
When I was a consultant in Southern California, I remember looking at some of the areas around Carbon Mesa in Malibu, and also the areas that affected PCH, very close to the ocean. And I found that the slope angle had a lot to do with the surface, like up in the upper portions of Carbon Mesa, where the slope was gentle, the surface was all black, okay? And whereas in the canyons themselves that were steep, the surfaces were broken. You had kind of more the pattern that we saw in some of your slides. And can you comment on those mechanisms about how the fire affects steep slopes versus gentle slopes, and on the generation of runoff and debris? I would appreciate that. Thank you.
Sure. I'll try to answer that by just reflecting back at the USGS debris flow likelihood model. It is slope driven. So that model, through an empirical correlation that was developed, it identified that slope is a critical component, and in particular slopes of 23 degrees that are burned at moderate and high is an independent variable that really drives that model. So that demonstrates that slope is a very important component. The other aspect that I would like to touch on, touching back on shallow landslides, is recent work done by Matt Thomas and others in the above the Thomas Fire in the Santa Ynez Mountains, mapped numerous landslides, over 10,000 landslides, and many of those had a slope inclination of around 40 degrees, which is fairly steep. So that's just one example of slope playing a very significant role in the hill slope response.
Thank you.
Josh, do you want to maybe address a little bit about dry ravel? And maybe explain that a little bit better for people who don't know what that is? Because that is obviously a very much slope-dependent factor.
Yeah, I mean, it's very, very slope dependent. So, yeah, you saw a couple images of dry ravel, of the accumulation of the sort of sandy, gravelly material in stream channels. And so you may ask, well, why does it end up there after fires? And probably the main reason is that it's very loose material, or most of it is typically loose material that has been sitting basically behind vegetation, held up. You can imagine behind the trunk of a tree, behind, it's here in Southern California, behind like a yucca bush, right? And it just accumulates in these little wedges all across the landscape because the landscapes are so steep that everything is at or above the angle of repose for that material. So it's only the vegetation that's just basically holding it there precariously, and then the vegetation burns, and you've taken away all those little mini sort of like, dams that are basically holding those wedges in place, and it all cascades down. Now, it doesn't all actually cascade down immediately. You go into these post-fire landscapes, and you listen, and you hear as little bits of gravel are cascading down. So it happens over, days to weeks, but it really is very highly slope dependent. That's one of the reasons one might argue for the gradient from rilling to ravel-dominated processes is just topography, right? Like where you have sufficiently steep topography, raveling becomes a dominant process. Where you don't, the sort of shallower slope areas you're talking about on some of the mesas, perhaps rilling is a more pervasive process. Rilling has its own slope dependence, but so it's a good point. The control on the process.
So thank you. Maybe we can get the last remarks for the last minute and then end the session. Is there a question? Okay, so we have.
Sorry, lightning round question. Appreciate you making the time. So really fascinating, really enjoyed the presentations from each of you. The question I have, we're talking about these hydrologic regime changes within these watersheds after the wildfire. How long does it typically take for the watershed to recover to like a pre-wildfire, regime, if that makes sense? Thanks.
I'll start off by, a lot of that depends on where you're at and the vegetation response. So if I'm in Montana, let's say near Glacier National Park, high rainfall rates, I have a wildfire go through, vegetation's going to come back in fairly quickly. 10 years after that fire, we've gone back and you're not even sure where the fire was, okay? Because everything grew back so quickly and so well. But if I'm in San Diego and a fire happens and I go back there 10 years later, I can still tell that footprint. Yeah, there's vegetation back there, but it's not fully mature. It's still visible. So it really depends on where you're located. Kind of the 3 to 5 years is a typical number that you'll hear, is that, okay, our watershed emergency is kind of over after about 5 years. I don't have to worry about that having big flood flows anymore.
Yeah, and absolutely right. The other aspect is just climatological effects. So for a great example is in 2020, it was a large fire season, and that was right around this 3-year drought that took place that was broke in 2023, if people recall. That 3-year drought really retarded the recovery curve. And we were able to track that through remote sense metrics that include leaf area index, NDVI, comparing burn scar areas with areas of similar topography, vegetative condition, and track how they recovered. So I would just indicate that it's, climate factors are also significant.
I'll just add one anecdote, which is that, I think to some degree, and I don't think we know this, but to some degree also it depends on the magnitude of like the forcing in terms of like a potential flood. We think that there's precipitation from the remnants of Hurricane Hillary, which was 2 years ago. It made its way up into Southern California. It dumped a lot of rain in the San Bernardino Mountains. And we think that one of the areas that had really substantial flooding was still because of a fire that was had happened 10 years prior, right? But that's like, it was an exceptional amount of rain, like 8 to 10 inches of rain, so in one storm, right? Smaller storms, you might not have known that the fire imprint might not have still sort of had any bearing, but we think it did that far out. So, I mean, I think like the 3 to 5 years is a good benchmark, but there can be a longer tail if you look in the sort of subtleties.
Yep.
All right. Okay, do you have any final remarks you want to add before we conclude?
For all the younger folks out there, there's still areas ripe for research. Don't ever forget that. We don't know everything.
Yes, post-fire, great point, and I can second that. I always indicate that this, in my opinion, is kind of a fledgling science. We're literally learning, designing the bike as we're riding it, kind of a scenario here. So I would really encourage people to get engaged in the post-fire research side.
Yeah, and I would just third that. I mean, you look at the USGS, you see these beautiful maps of reds and oranges and yellows and think, well, we know what's going on here, and we do, that those are great tools, right? And they're the best tools we have. There's improved versions coming out, but underneath them, there's a lot more to be done.
Yep.
Thank you to all the speakers, and thank you for being here. Let's thank them one more time. And